Good day, everyone. My name is Nicole G. Beltran, and I am your reporter for today. So, my topic is all about geological map interpretation. So, let us first define what is a geological map. So, it refers to a map that shows the distribution of different types of geological features within a particular area. So, when we say geological features, it refers to geological structures that are already discussed in the previous reports, but we will still review it in my report because these geological structures are very important as it is included in the interpretation or in the process of interpreting the geological maps that follow. So what I am referring to as geological structures are also called outcrop patterns. So we all know that outcrops are areas of rocks that are exposed at the surface or beneath the surface. So we have here the first three outcrop patterns. The first one is the horizontal beds that has an outcrop that follow the contours because they are at a constant altitude. So if we see an outcrop, if that outcrop follows the contour, like what is projected in our right side, as we all see, the sign for horizontal beds is this. So if we so the letters G, H, I, and J are horizontal beds because as we can see, the shape of the outcrop is projected along the lines of the contours. So if we see an outcrop like that, if before we um before we interpret it as a horizontal bed, we have to consider the contours. So if the contours are like that, if it follows the shape of the outcrop, that means that the outcrop has a horizontal bed. But if the outcrop cuts across the contours, say if the contours is shaped or is projected like that, so as you can see, the outcrop is cuts across the contours. So when we see in an outcrop like that. So let's assume that this is a straight outcrops. So that is probably a vertical beds because vertical beds have straight outcrops that ignore the contours. So when we see straight outcrops in the map and it ignores the contour, that is probably a vertical bed. So if we see curved outcrops like that, if we see outcrops like that and it cuts across the contours, let's say the contours are like that, it cuts across the contours and it is curved, that is probably a dipping bed. So as we can see on our right side, we have different surfaces that shows different outcrop patterns. So as we can see on A and B, it has the sign of a vertical strata or vertical bed. So it makes sense because its shape is just straight, right? So also it cuts across the contours that is represented by the broken lines. So it makes sense that it is a vertical bed. So C and D, also E and F, has the sign of a strike and dip. It also makes sense because it has a curved outcrop as you can see on its top views. It has a curved outcrops or a V-shaped outcrop like this D and F. It has a V-shaped outcrop and also it cuts across the contours. So it makes sense that it is a dipping bed or it represents a strike and dip. So on G and H and also I and J, it represents a a horizontal strata or horizontal bed. It makes sense, right? Because as you can see, the outcrop shapes are straight and it follows the contours as what we defined earlier. So it is a horizontal bed. So I and J is also a horizontal strata or a horizontal bed because um no matter how it is shaped, no matter its V shape, it still follows the contour lines. So most probably it also represents horizontal beds. On the previous slide, we discussed about dipping beds, but we didn't mention the direction of the dip. So in this slide, we are going to discuss dip direction by the V in valley rule and by succession. So the V in valley rule can be done by recognizing valleys on the map. So valleys can be represented by topographic maps that are shaped like V's. So for example, this is the topographic map and the topographic contours. I mean, so when let's say these broken lines are the topographic contours, and also a valley can also be recognized when there is a river flowing in that V-shaped topographic contours. So when we see that, that means that it is a valley. So when that valley passes through an outcrop that is also shaped like V, so for example, we have an outcrop that is shaped like V here. So that means that that particular outcrop has a dip in that area. So the direction of the dip, when we see an outcrop like that, a V-shaped outcrop, the direction of the dip is towards the tip of the V of the outcrop. So we must always remember that we must base the direction through the V of the outcrop and not the V of the topographic contour. Because there are instances that it is not always like this. There are instances that the topographic contours are shaped like this, like that, and there are rivers, and the outcrops might be shaped like that. So we must always note that the direction of the outcrop is the direction of the dip is always based on the tip of the outcrop. So in this case, the direction of the dip is in that way. So for easier way in visualizing this concept, let's imagine that the V-shaped outcrop is an arrowhead. So it is easier for us to visualize or to identify the direction of the dip because if we imagine it as an arrowhead, so that means the dip is already pointing in that way and that way. So automatically the dip is in that way because the outcrop is pointing that way. So in this case, the dip of the outcrop is pointing that way, right? Because if we imagine it like an arrowhead, so it is pointing in that way. So regardless of where is the direction of the flow of the water, we must always base our interpretation on the V-shaped outcrop regardless of the V-shaped contour and regardless of the flow of the river. So always remember that. So the dip direction by succession is done by first consulting to our stratigraphic column, or most commonly called as our legend. So it is indicated in our legend the succession, or it is indicated the sequence of the layers of the rocks beneath our surface. So let's say this is our legend. This is our legend, and this is the older rocks, and this is the younger rocks. So if we see the map, if we recognize that this is the younger a younger outcrop that is projected in our legend, and this is an older rock. So most probably our dip direction is in that way, because it is stated that the dip direction by succession is always pointing at the younger rocks. So this is the younger rocks, right? This is the younger rock outcrop. So the dip direction is pointing that way. So if we project that to our cross section, let's say this is our cross section, and the dip direction is pointing that way. So if we project that layers here. So our dip direction is pointing that way. So most probably the layers of our rock outcrops would be shaped like this, because the direction, or the dip direction, is pointing that way. So I didn't mention it in the earlier slides, but dip creates an angle within the horizontal. So if it is pointing in that direction, it creates an angle within the horizontal. So this is what it means to identify the dip direction through succession. So let's proceed to the succession of rocks. So there are two kinds of succession. First is the inlier. The inlier is when old rock outcrops is surrounded by outcrops of younger rocks. So how does it happen? It happens when a valley is created. So for example, this is a valley, and the valley has a horizontal bed. Let's say this is the bed of the valley. It has a horizontal bed. In most cases, the older rocks are always beneath the is always beneath the younger rocks. So let's say this is the older rock layer, and this is the younger rock layer. So in this case, it is a ridge, right? And it is a case of inlier, because this older rock is exposed to the younger rocks. It is surrounded by the younger rocks that are above the older rocks. So it is a case of inlier. So another case is when an anticline. So an anticline is an ano. An anticline is an upward fold. So when that anticline is being eroded, so when that part is being eroded, most probably this would be um this would be left. So this is the older rocks, or this is the older rock layer, and this is the younger rock layer, and the older rock layer is surrounded by the younger ones. So this is a case of an inlier, because the older rock layer is surrounded by the younger rock layer. So the second one is the outlier. So the outlier is when the younger rock outcrops is surrounded by older rock outcrops. So in most cases, outlier is being shown a syncline that is being eroded. So let's say this is a syncline. Syncline. So when that syncline is eroded, let's say this part is eroded, so most probably this would be left. And this is the younger layer, right? And this is the older layer. So the younger layer, this younger layer is being surrounded by the older layer. So this is a case of an outlier. So the width of the outcrop can also identify if the dip is steep or not. So for example, we have a map and it shows a outcrop like that. So when we project that to our cross section, say this is our cross section, we project all of that, project. So as we have observed, this part, and this part are has greater width. This outcrops has greater widths compared to this one. So this one has a narrow dip. So that indicates um what do you call this? That indicates the slope of the dip. So when we project this in our cross section, most probably the shape of our outcrop beneath the surface is like that. Like that. Yes, like that. So as we can see, the slope of this part on this part is steep, and on this part is um just it has a low dip, meaning the angle of the dip is just small. So the width of the outcrop identifies if it is a low dip or a steep dip. So when the width of the outcrop is greater, that indicates a low dip, or the angle of the dip is small with respect to the horizontal. But when the outcrop has a narrow dip, when the width of the outcrop is narrow, that indicates a steep dip, as what is shown in our drawing. So unconformity. Unconformity is happens when younger outcrops cuts across the ends of outcrops of older beds. So this happens when a folded layers of rocks gets eroded. So when that folded layers gets eroded, let's say it gets eroded and gets like that. And when it experiences deposition, um, these older layers will get will get covered by the younger layers. So that is what we call unconformity. So faults cuts across outcrops that displaces the outcrops. So let's compare two surfaces that has no fault and has a fault. So let's say this is a surface, and when this surface has a fault, let's say there's a fault there. So as time goes by, this surface, when it has a fault, would as time goes by, it would displace the outcrop. So let's say after how many years this would be the result of the fault, it would the this is an outcrop, and as time goes by, when there is a fault in that particular surface, it would mura siya iisbog. Ang outcrops would move as time goes by when there is a fault in that particular surface. So faults are divided into two kinds. So first is the anticline, which I already showed it earlier. So an anticline is an upward, yes, it is an upward anticlines. It's like a hill. So a syncline is a downward layer. It's like it's folded downward. So that are that are the two kinds of folds. These are geological map symbols that are commonly used in interpreting geological maps. So, as you can see, the dip, its direction, and its amount in degrees is this one. So, it is represented by an arrow and a number in degrees. And horizontal beds are represented by this. It's like a cross symbol, and a fault that points on the down throw side is this one. And vertical beds, um, this symbol is represents vertical beds. And syncline, this is the symbol for syncline, and this is for anticline. And these boxes that you see represents the different rock materials that can be found in rock outcrops. So this is for alluvium, sandstone, limestone, till, shale, and igneous rocks. So these are the common geological map symbols that we can use in interpreting geological maps. So there are stages of interpreting geological maps, and these are to identify the following. First is the structural breaks like faults and unconformities. The second one is dips by succession and V and valley rule. The third one is the succession of rocks like the inlier and the outlier. The fourth one is the fold axis such as the syncline and anticline. The fifth and sixth one is the stratum contours if further details are required. And the sixth one is the cross section, which shows subsurface structures. So the fifth and sixth one will be discussed in the following slides. So we have here a given geological map of Scar Hill. And as you can see, interpretations are already given. And all of these interpretations are just initial interpretation because it only follows the stages 1 to 4. So the first step would be identifying structural breaks such as faults and unconformities. So as we can see, um, the fault here is already given, and the tick is pointing in that way. So that means that in this side, in the left side, this is the side where it moves downwards, and on the right side it moves upwards because this tick here identifies the side where the outcrops would move downward. So as we have observed here also, it states that it is an unconformity. So most probably the sandstone, which is this, and the clay, which is the green ones, experience erosion, and the limestone, which covers the clay and the sandstone, experience deposition enough to cover the two older rocks. So the second step would be to identify dips by the V in valley rule and by succession. So as we can observe, the topographic contours in this part are shaped like V. And also there is a river that is specified in this side. It is colored in blue, and also this side and the topographic contours are also shaped like V. So starting with in this side, the valley, so it indicates a valley, right? Because the topographic contours are shaped like V, and it is there is a river flowing in this side. So at the same time also, the valley passes outcrops that are shaped like V. So um specifically this outcrops, I this not clear. So this outcrop are shaped like V, this outcrop are shaped like V, this outcrop are shaped like V, and this outcrop are shaped like V. And timing also that it there is it the valley is passing through this series of V's. So the direction of the dips in these V's are pointing in the tip of the V. So in here the dips are pointing that way, and here also the dip is pointing that way because the tip of the V is pointing that way, and here also, and in here is the opposite because the V is pointing in the opposite side. So while on the other side of the river, we also have a valley because the topographic contours are shaped like V, and we have a river, and also the outcrop are shaped like V. So we have a dip that is pointing that way. So how about the dip dip direction by succession? So as we can see, there is no stratigraphic column that is given in the projected geological map. So there is no we cannot identify any dip through succession because we need the legend or the stratigraphic column to identify dips by succession. So we observe there is no dips that are specified here through succession because the succession is not specified. So the third step also, which is the succession of rock layers, cannot be also identified in the following geological map because, as I've said earlier, there is no stratigraphic column that we can use to identify the succession of the rock layers in the given geological map. So let us proceed to the fourth step, which is identifying fold axes. So as the fourth step is the fold axis. So as we all have remembered, the fold axes like the syncline and anticline can be identified by recognizing the change in direction of the dips. So as we have observed, the dips are starting from here, from this side, the dips are pointing that way, and suddenly when we arrived in this side, the dips are opposing the direction. So the dips have shifted direction. So most probably there is a fold axis this that are lying between this side in between this side and this side, because there is a change of what do you call this, direction of the dips. So we can recognize fold access by putting a sign in between the change in fold axis. So if we draw it in our ano, let's say this is our map, and we all know, or this is our cross section, so we all know that the dip here is like that, and dip here is like that, and dip here is pointing that way. But suddenly in this side the dip suddenly points that way. So in between the two directions that are opposing, so there would lie the fold axis. So if we visualize this in our cross section, if the if the dip points that way, that the shape of the, or the direction of the outcrop here, if the dip is pointing that way, the shape of the outcrop would probably be like that. And also in this way, the shape is like that, and this is like that. So if this one is opposing, the shape would be like that. So if we join that two, that would if we join that two shapes of outcrops, it would probably result to a shape like this. So what is this shape? So this shape is a syncline. So probably in between these two these two dips lies a syncline. So if we visualize that in our cross section, this would probably be like that, like that, like that. I know, no. So that would create a syncline like that, because they are two opposing directions. So as you can see in our geological map, there is already a syncline that is indicated. So this is the sign of the syncline. So our interpretation is correct. So this is another geological map, and this is the geological map of Okunder. I'm not sure of this pronunciation, but it is the geological map of Okunder. So as we have observed, this geological map already has a stratigraphic column, or what I previously referred to as the legend. Um, Yes, we commonly call it as legend, but if the stratigraphic column, it's like a technical term of the legend, because it is much detailed, and it is what we primarily view or read before interpreting the map, because the informations that are stated in the map is given or is stated in the stratigraphic column. So as we can see on the left side of our map, the stratigraphic column states the scale of the map. The units of the scale is represented in kilometers. So from 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 this point to this point, it is 1 kilometer, and from this point to this point, it is 2 kilometers. So if we want to measure the distance between 2 points are everywhere on this map, we are just going to use this scale to know the actual distance of the 2 points that you have chosen to measure. As you can see, the succession is already given in the map, and the one that is underneath all of the layers are the oldest rock outcrop, and this is the slate, and then it is followed by the limestone, and then the next one is the shale. And we have three kinds of shale here, three layers of shale. So following the limestone is the shale, and then next one is the Oconder grit, and then the shale 2. The next one is the Belvoir grit, and next is the shale 3, and the youngest rock outcrop is the coal measures. So all of these are layers of rock outcrops that can be seen beneath the layer of this area. So the thickness of this rock outcrops are also specified in the stratigraphic columns. So as we can see, the scale of the thickness is in the units of meters. So this 300 meters, 600 meters, 900 meters. So the units are in meters. So because this is given in the left side of the succession, so we can we can proceed with the step 4 and 5, because the thickness of each layer is needed in determining the stages 4 and 5 in the stages that are given in the previous slides. So what else? This is also given the alluvium and the dolerite, but the alluvium and dolerite is not necessarily a part of the succession, because murara manggod siya nisuksok sa mga rocks. So it's like a dike. We all know that a dike is a rock, but it only cuts across the other rocks. So as you can see in the map, the dolerite and the alluvium just cuts across the other rocks. So also the symbols that are used in the map are also specified in the stratigraphic column. So this arrow with a number represents the depth direction, and also its values in degrees. So that's the symbol for the depth, and the line here represents the fault. So it is clearly drawn in the map that it has a fold in this area. So the broken lines represents the rivers. So the topographic contours are not given. Instead, the rivers are used to identify valleys. So the north, in most maps, um the the north direction is um the one that is given instead of the whole north, south, east, west. The north is just projected in the stratigraphic column. So that is how we read a stratigraphic column. So after interpreting the stratigraphic column, we are going to proceed for the geological map interpretation. Remember, our first step is to identify the um, structural breaks that are present in our geological map. So the first stage, or the first step, is already evident in our map because it is clearly stated that it has a fault here. The line here represents the fault. So what else? So I don't think there is a unconformity in this map. So I conclude that there are no unconformity because I can't see any layers that are completely covered by younger rocks. So let's proceed to the next step, which is identifying dips through V in valley rule and the succession. As we can see, there is the broken lines represents the rivers. Therefore, there is a valley there. And then we will recognize dips in that area. So as we can see, this is a V. This is a V. This is also a V. This is a V. What else? This is also a V. But I'm not sure of my interpretation. We will check my interpretation on the next slide. So this is also a V, but there's already a dip that is indicated. So that's also a V. This is also a V. So before we identify any dips that are identified using succession, first we're going to determine if the shales are shale 1, shale 2, and shale 3 in order to visualize if the map has a succession. In this part, in between the coal measures and the Belvoir grit is shale 3. So this is shale 3 in between the coal measures and the Belvoir grit. So in between the Belvoir grit and the O'Connor grit is the shale 2. So this is shale 2. And then in between O'Connor grit and limestone is shale 1. So this is shale 1. And then in between again with limestone and okay, this is shale 1 also. And also in between O'Connor grit and Belvoir grit is shale 2. So this is shale 2. In between Belvoir grit and O'Connor grit is shale 2. And how about this? So how can we identify the shale in this side? So Belvoir grit, shale 2, O'Connor grit. So this is probably shale 1. Now that we identified the shales, or we have specified the shales in each um, kind of shale, so we are now ready for identifying dips by succession. So we are going to look at the stratigraphic column. So as we recall, dips through succession are pointing through the younger layers of rocks. So as we can see in our stratigraphic column, coal measures are the youngest, and then followed by, this is the coal measure, followed by the the shale 3 here, and then followed by the Belvoir grit here, and followed by the shale 2, which is this, and the O'Connor grit, and followed by the shale 1. And last one is the limestone. So the slate is not visible, so it is probably beneath the surface of this area. So we identified the succession in this area. So most probably the dip is pointing that way. So that is a dip that we can identify through succession. So how about in this part? So this is limestone, shale 1, O'Connor grit, and shale 2. Also shale 2 and also Belvoir grit. Shale 3 is not visible. So we are going to stop here in the Belvoir grit. So where did we start? We started here in the limestone. So therefore, we have a dip. We can identify a dip in that direction. So there is a dip we can identify in that direction. So that's a dip by succession. So how about in this part right here? So this is Belvoir Grit, this is Shale 2, this is O'Connor Grit, and this is Shale 1. So the youngest is the Belvoir Grit. So most probably we have a dip that points that way. So we are done with the stage 2 of identifying dips that are identified using V in valley rule and through succession. Let's proceed to the identification of fold axes, which is the syncline and the anticline. So syncline and anticline is identified by recognizing the changes in the dips in the map. So we will observe the changes in the direction of the dip. So as we can see in this area, it is all pointing in the right side. So in this area, direction of the dip opposes the direction in this side. So in this side is pa right, and then pagapot diri na side is pa left. So how about in this side? So in this side, it opposes to the direction in this side. So conclude we can conclude that there is fold axes that are visible in this geological map. So it's probably on this side. The direction of the dip, if we will view it in a cross section, would be like that. And then in here, the direction of the dip would be like that. So therefore, we can create, if we combine these two direction of the dip, we can create a syncline in this side. So we will establish in between these two opposing directions, we will put a syncline sign. So it probably be like that. There is a syncline sign here. And how about this side? These two opposing dip direction also specifies fold axis. So if we visualize it in a cross section, it would probably be in the shape of in this side. And this side would be like that. And on this side, since it is pointing that way, so it would probably be like that. So if if we combine the two dip direction of the outcrop, therefore we can create a shape like that. So we can conclude that that would be an anticline. So in this side of the map, we can conclude that there is an anticline in this side. So anticline sign, anticline, it is an anticline. We are done with the 4 stages of map interpretation. Therefore, we should check our interpretation on the next slide. So this is an actual interpretation of the geological map that we have interpreted last slide. So I've copied it in this slide in order to recognize the parts where we omitted one of the process, and also the stratigraphic column to guide us in further interpretation of the geological map. So we are correct that there are dips in here by V in valley rule, and also in here. So we are correct in that part. How about the dips by succession? So we are correct that there is a succession here, succession, or there is a dip by succession. And also we are correct that there is dip succession here because it is also indicated here. And we are correct with the syncline that we interpreted here and the anticline that we interpreted here. So um, the data that or the process that we omitted is the succession by rocks, which is the inlier and outlier. So we are going to interpret it here. So as we can see, this part, the shale 3, is younger and it is surrounded by a Belvoir grit which is older. So this is a case of an outlier, right? Because the younger is surrounded by the older. What else? Also, this is the dolerite is a vertical dike because it is just straight. So it is a vertical dike because it is called dike because it cuts across the other rock outcrops. And also, this is a thin alluvium which has a depth that is unknown. So the depth is unknown because I think that mura siyang nipatong sa rock. So we have a fault here that displaces the two outcrops. So it is just a small fault that its displacement, the displacement of the two outcrops is indicated by the throw, which is less than the thickness of the shale 2. Also, I forgot about the width of the outcrop. So if if the width of the outcrops is greater or wider, it means that it has a low dip, and if it is narrow, it indicates steep dip. So in this side, the outcrop the dip is low because it has a wide outcrop, and in this side it has a narrow outcrop, so it indicates a steep dip. In this outcrop also, it is great, the width is super great, so it indicates a low dip. So these dips that has a number in it are already given. So I think we are already done with the interpretation of this geological map. 3-point interpretation. So this stage of interpretation is only done if further details is required because borehole survey is done before we can proceed with this interpretation. Through that borehole survey, we can obtain the elevation of the borehole which is needed in this process, and also um, they will obtain this geological borehole layers that shows the different layers of outcrops. So a minimum of 3 isolated points are plotted in a single horizon using borehole data. So using the data that are obtained from the borehole survey, those points will be plotted in this process. So we have to assume locally uniform depth. So in this case, you assume that the depth is in the direction directed that way. So within these boundaries, or within these 4 boreholes that are chosen, the depth would all be pointing that way. So draw lines between any pair of borehole and distribute altitudes that have uniform intervals. So as you can see, in this case, they have chosen 4 boreholes, and this borehole is the elevation of 40, this is 15, this is 12, and this is 48. And we are going to draw lines between any pair of these boreholes. So how would you know um if where would you draw the lines? Because pwede naman dito ka mag-draw ng lines. So as I have observed, on the problems or the examples that I have encountered, um, they draw lines on the pair of boreholes that have a huge gap or that has a considerable gap in terms of elevation or altitude. So, as we observed, this 15 elevation is just compared to the other elevation is just lower. Their gap is just lower. This 15 and 12, their elevation gap is lower. So how about this 40 and 48 elevation of boreholes? So as we have observed, compared to the other elevations, their gap is lower also. So the lines, as you have observed, the lines are drawn between this boreholes, which is 15, an elevation of 15 and 40, and an elevation of 15 and 48, and an elevation of 15 and 12. So as you have witnessed, the lines are drawn within the pair of boreholes that are that have a huge gap in terms of elevation, so that we can proceed to the process of distributing altitudes that have uniform intervals. So, after drawing lines between the pairs of boreholes that have huge gaps, so we are going to distribute elevations within these boundaries or within these lines. So, the distribution of points that has a uniform interval, let's say in this case is you have chosen an interval of 10. So this process of distribution is done by interpolation, meaning the points that you have chosen, it is only estimated using the given elevation. So you are just going to estimate um the elevation between those boundaries or between those lines. So yes, after we have distributed points within that line, so let's say we have 4 points there. So we draw lines and we have distributed equal what do you call this, equal altitudes or elevation. Then afterwards you are going to connect points with the same altitude, creating a line or curve. Let's say in this case we're going to connect, so and the dip is going that way. So if you're going to connect, as you can see, it creates a curve. So in the case above, it created a curve also, right? As you have observed, it created a curve, and it does make sense because the dip is going that way. The dip is going that way, and it's like creating, if we further expand those points, it's like we will going to create a V. So it makes sense, right? So if in the survey they have only chosen 3 points. Let's say this is the 3 points, 1, 2, 3, that's the 3 points that they have chosen. So if they have only chosen 3 points in the borehole survey, that means that um the lines, or if we connect it, lines are only created but not curves. So as we can see in this, it only created a straight line because it it is only the boreholes are only 3. So if we have more than if we have more than 4 boreholes, therefore we can draw curves, and it can reveal. By the way, that curves that we have created are called the stratum contours. So stratum contours are like this, as what is shown in the image below. Stratum contours are like Stratum contours are like topographic contours, except that they show the shape of buried geological structures. So this lines here, this curved lines here, represents the shape of the geological structures that are underneath our our surface. So let's say this is the surface that we have chosen to as a medium for our 3-point interpolation. Let's say we have chosen in this part. So let's say this stratum contours that are shown is represents these stratum contours, but it is only limited because we only chose 4 points. So that represents the stratum contours which are only shown at the top view. Yes. The next stage of interpretation shows not only the top view, but it's like showing the front view. So let us proceed to the next stage of interpretation. So our next and probably the last stage of map interpretation is drawing the geological cross section. So this stage is like revealing the structure of what's underneath the surface of our geological map. So let's start with the simplest example. This one here is a portion of our geological map of Alconder Grit. So so the first thing that we will do in drawing geological cross section is we will going to draw a line from which we will going to slice the surface in order to reveal what is under that surface. So in this case, the line of section is already given. So in this part, so after drawing a line of the section, so we are going to project the outcrops that are exposed on the surface. So in this case, from here to here, we are going to project that outcrop, let's say below. We are going to project that outcrop below our um map. So from here to here, we're going to project, and after we projected it, we are going to identify the thickness of each layer. So in order to identify the thickness of each layer, we are going to need the help of the stratigraphic column. That's why I included it in here. So the dip is pointing in that way, right? So that means that it is pointing on the younger outcrop. So that means that this shale is shale 3 because it is younger, and this shale is shale 2 because it is older. So the thickness of our shale 3 is it's like 50 meters to be estimate. Let's say this is our 100 meter, 100 meter, and 100 meter. So let's say this starts with 0, and this is 100, this is 200, and this is 300. After that, we all know that the oldest here is the shale 2. And as we estimate it, it's like um 75 meters as we estimate. So if we project it in here, so let's say this is 75 meters, and we will going to project that in that. So um the point where they intersect is where you will make a you will plot a point. So the second one is the Belvoir width. So I estimate it as a 100 meters. So let's say with respect to shale 2, Belvoir width is 100 meters up to here. So if I'm going to reflect that through here, so this is where the point where they intersect. So the third one would be the shale 3, which I estimate to be um thickness of 50. So let's say this is 50. If I project that, so this is the height of shale 3 with respect to the other rocks. So if we will going to connect all of that, so if we're going to connect that, the this would be um this would be our cross section. So let's say that is our cross section. So to draw it clearly, let's say this is our cross section. And then we have points 2, I1. Let's say this is point 1 and this is point 2. So after establishing the points, we are going to um, project or wait, we are going to project the thickness of the Belvoir grit. So I have estimated earlier that the Belvoir grit is 100 meters. So let's say this is 100 meters. This is 100 meters. And then afterwards, we are going to recognize the dip. So the dip is in that way. So most probably, the dip would be slanted in like that. So if we consider the thickness of our outcrop, it is wide, right? So most probably it has a low dip, and it is it the in its slope is just smooth. So we will connect this line, these 2 points, so it will result to that outcrop. So probably this would be the structure of our um map underneath it, underneath its surface. So let's see. So our interpretation is correct, but it's not that accurate, but at least we have visualized it. So this is another example of drawing geological cross section. So this is a complicated one, but we are just going to follow the procedure of drawing a geological cross section. So the first thing we're going to do is to project the lines, right? So we're going to project the lines. So I know we are going to, since the section line is already identified here, so what we're going to do is to project the lines. Project, project. So let's say this is our projected lines. This, 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 this part, 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 and a lot of parts. So let's say that's our projected points. So after we have projected it, the next thing we're going to do is to look at our stratigraphic column, and we will going to base the thickness of each layer on our stratigraphic column, and we will draw it on our side. So we will going to draw it in here on the left side, so that we will know the thickness of our stratigraphic column. But we also, but the sec another way is that um we also need to base the thickness. We also need to look at our stratigraphic column to know the thickness of each layer, and after that we are going to project on we are going to project downwards of each of the projected points on its surface. We are going to project downwards its thickness. So let's say this is the thickness of the projected points on the surface. So this is the projected thickness, this is projected thickness. So let's say we've already projected the thickness of each of, and that's wrong, the thickness of each of our the thickness of each of our layers. So after projecting the thickness, it is safe for us to connect, or no, let's first let's first consult our initial interpretation in this in this map. So we have assumed that in this part we have a syncline. So it is now safe to draw um our layers. And also in this part, we've assumed an anticline. So it is already safe to assume or it is already safe to connect our thickness. So in this part, if we're going to project the syncline, or the line of symmetry of the syncline and the line of symmetry of our let's say line of symmetry of our syncline and anticline. So if that's the case, we are safe to draw that this is downwards. This is downwards. This is downwards. And when we pag-abot diri na point, pwede na ta mag-upwards. We will going to be to draw it that is directed upwards. Directed downwards, then upwards, downwards, then upwards, downwards, then upwards, since we already know that it is a syncline. So in this case, pag-abot na sa diri na point, magpa-downward na sad ta. downward, since this is an anticline. Downwards, 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 downwards. So we are going to look at the symmetry. We all know that um we all know that the rock layers in this part is the same with this part, the same with the same with the right part. So it is safe to assume um that this surface is got eroded down. So the broken lines is the representation that this surface is an anticline that got eroded. So that's our interpretation. So after that, we also have to recognize the fault. So this is the fault. So af- after drawing it, so we have to adjust our layers. So this being in downwards and this being in the up, it is displaced upwards. This side is being displaced upwards and this side is being displaced downwards. So what else can we conclude? So the dikes, which is the dolerite, and the alluvium, which is that cuts across our rock layers, is also projected in our cross section. So this is this vertical layer here represents our dolerite dike, and this yellow part, this tiny part of alluvium here, is the alluvium. So yes, that's our interpretation. So the broken lines. The broken lines makes it easy for us to visualize the structure of our surface, right? So all of this, um, all of this, all of the outcrop patterns or the geological structures that we have used in throughout our interpretation is really useful because it helps us to visualize the subsurface structure that are beneath the surface of our earth. So that's why it is important to note all of those structures in interpreting geological map structures. So before I end my presentation, let's just have a brief review on the things that we have learned about the interpretation of geological maps. So we have 6 stages of interpreting geological maps. So the first four is to identify the geological structures that are present in our geological maps. The first one would be the faults and unconformities. The second one would be the dips, which is identified by the V in valley rule, and the second one would be the succession. The third one would be the succession of rocks, which is divided into two, which is the outlier and the inlier. The fourth one is the fold axis, which is the syncline and anticline. So the fifth stage is drawing the stratum contours through the 3-point interpretation. So the stratum contours only shows the top view of our um, rock outcrops. So the sixth stage is the drawing the cross section of our geological map, which shows the front view of our geological map. So it's like revealing the structure of the surface that is beneath our geological maps. So that would be all for my report. And these are my references that I used in compiling my report. So thank you so much and God bless.